Hey there, welcome back to the Deep Dive. Today we're exploring complexity science.
Oh, very cool.
And you've sent over a whole bunch of articles and research on this topic, so I'm
Yeah.
guessing you're ready to kind of get down the rabbit hole
Absolutely.
with this one.
What's captivating about complexity science is how it kind of bridges so many different areas,
Yeah.
biology to economics, even politics.
Wow.
It's all about how order arises from what seems like chaos,
Right.
from systems with tons of moving parts
Yeah.
interacting.
Okay, so we're not just talking about complicated stuff.
Right.
We're talking
Yeah,
about complexity,
exactly.
like how a single cell becomes a human,
Mm-hmm.
how ecosystems work together
Yeah,
with millions of species, or even how stock markets behave.
exactly. And one of the big names in this field is Stuart Kaufman.
Okay.
He suggests that understanding complexity can help us redefine what we consider sacred.
Redefine what's sacred.
Yeah.
That's pretty deep.
It is, yeah.
What does that even mean?
Well, Kaufman uses this example of the Kiowa tribe's sacred shield.
Okay.
It was stolen after a battle and then recently rediscovered.
Wow.
And its return brought a sense of healing and value back to the Kiowa people.
Mm.
He thinks complexity science could do something similar for humanity.
Like, help us find meaning in a world that often feels random and chaotic.
That's the idea.
Hmm.
And it gets even more interesting when you consider how it challenges our assumptions about the universe.
Okay.
We usually think about things moving towards disorder, right?
Yeah.
Entropy, things falling apart.
Hmm.
But complexity suggests there's another side to that coin.
You mean, like, how can we have so much order if everything's supposed to be running down?
Right. The second law of thermodynamics says the universe is heading toward heat death
Right.
and maximum disorder.
Yeah.
But look around, we see incredible order everywhere.
Yeah.
Cells, ecosystems, galaxies.
So how do we get this complexity, this
Yeah.
order,
Yeah.
without someone or something directing it?
That's where self-organization comes in.
Okay.
It's the idea that order can appear spontaneously without a central control.
Hmm.
Kaufman uses the example of a whirlpool in a bathtub.
Okay.
It keeps its shape even though the water's constantly flowing.
Okay, I see that.
Yeah.
So it's not like the water molecules are being told to form a whirlpool.
Right.
They just do it based on how they interact.
Exactly.
And we see this kind of persistent self-organization in other places too, right?
Think about the Great Red Spot on Jupiter,
Oh, yeah?
a giant storm that's been raging for centuries.
Yeah.
It's a stable structure, even though the individual gas molecules are constantly shifting.
That's amazing.
Yeah.
And, you know, another thing that really stood out in the research you sent was this idea of the Cambrian explosion.
Ah, yes.
Yeah.
A truly pivotal moment in Earth's history.
Yeah.
About 550 million years ago, there was a sudden surge of new life forms.
Okay.
Practically all major animal body plans, or what scientists call phyla, popped up in a relatively short amount of time.
And what's weird is that the most complex body plans showed up first,
Yeah.
which doesn't really fit with the idea of gradual Darwinian evolution, does it?
It's a real head-scratcher for traditional evolutionary theory.
Right.
Kaufman proposes that life evolves toward the edge of chaos,
Oh,
a kind of balancing act between order and chaos.
so it's like life needs structure, but also flexibility.
Yeah.
Too much order and things get stuck.
Right.
Too much chaos and nothing can develop.
Exactly.
Is that like finding the sweet spot for evolution to take off?
Exactly. It's a sweet spot that balances structure and adaptability.
Yeah.
The Cambrian explosion could be a prime example of what happens when a system hits that sweet spot and explodes with possibilities.
All right, so we've got self-organization, this edge of chaos,
Yeah.
and the Cambrian explosion.
Yeah.
Now let's zoom in on something even more mind-boggling.
Okay.
How a single fertilized egg develops into a whole organism.
Yeah.
What's called ontogeny.
Ontogeny is a truly remarkable process. A single cell, packed with genetic instructions, divides and differentiates to create trillions of specialized cells that form a human body.
And there are all these feedback loops.
Yes.
Signals, genes switching on and off in precise sequences.
It's incredible.
Yeah.
How is all that information contained in one tiny cell?
It's incredible, right?
It is.
Early scientists were really puzzled by this.
Yeah.
One experiment that really challenged their thinking involved frog embryos.
Okay.
This German biologist, Hans Dreich,
Oh, yeah.
separated the cells of a frog embryo at the two-cell stage.
Okay.
He figured he'd get two half-frogs.
Right. Right.
That seems logical,
Makes sense.
but I bet that's not what happened.
You're right. He ended up with two completely formed, although smaller, frogs.
Wow.
Yeah.
So it's like the cells had this hidden potential
Mm-hmm.
to adapt and change based on their interactions, not just follow a fixed blueprint.
Yeah.
Which brings us back to complexity again, right?
Exactly. Development isn't just about following instructions.
Yeah.
It's about cells communicating, responding to signals, and self-organizing to create the intricate structures of a body.
Now, if we rewind the tape even further,
Yeah.
we hit the ultimate complexity question,
Yeah.
the origin of life itself.
Right.
How do we go from basic chemicals to self-replicating, evolving organisms?
One of the biggest mysteries in science.
Yeah.
We've got some clues, though.
Okay.
Back in the 1950s, Stanley Miller did this famous experiment
Yeah.
that showed amino acids, the building blocks of proteins,
Right.
could form from simple gases under conditions like the early Earth.
So that showed that life's basic ingredients
Yes.
could come from non-living stuff.
Mm-hmm.
But how did those ingredients assemble into something that could replicate and evolve?
That's where it gets tricky.
Yeah.
One idea is the RNA world hypothesis,
Okay.
which suggests that RNA, not DNA, was the first carrier of genetic information.
Because RNA can carry genetic information and act as an enzyme, speeding up chemical reaction.
Exactly.
So could those early RNA molecules have been replicating themselves, kicking off evolution?
That's the thinking.
Mm-hmm.
But going from simple molecules to a self-replicating system is still a giant leap.
Right.
That's where Kaufman's concept of collectively autocatalytic sets comes in.
Okay.
He thinks that if you have a diverse enough mix of molecules,
Yeah.
the odds of a self-replicating system appearing go way up.
He uses this analogy about buttons and threads, right?
Yeah.
Can you explain that? Imagine you have a box full of buttons and threads.
Okay.
If you have enough and they connect randomly,
Yeah.
you might just get a set of buttons that form a closed loop, a self-contained structure.
So are the buttons like molecules and the threads are chemical reactions?
Yes.
Okay.
And if you have a lot of different molecules and reactions, the chance of a self-replicating loop,
Yeah.
like a basic metabolism, goes up.
That's pretty wild.
Yeah. And Kaufman calls this supracriticality, right?
Exactly.
Like when a system hits a tipping point and suddenly explodes with diversity.
Exactly. And that's what might have happened in the early evolution of life.
Okay. I'm starting to see how this complexity idea plays out.
Yeah.
Now can we switch gears
Sure.
and look at how complexity helps us understand how our genes work?
One really fascinating area is the study of genomic networks.
Okay.
All the interactions between genes that control everything from how we develop to diseases.
Right.
Scientists are finding that these networks can be modeled
Okay.
using what are called Boolean networks.
We're Boolean networks.
Yeah,
Aren't those the ones where genes are like light bulbs that can be on or off?
you got it.
Okay.
And the connections between the light bulbs show how genes regulate each other,
Okay.
turning each other on or off.
And the amazing thing is that these simple models
Yeah.
with just on and off states can show us how real genomic networks behave.
It's pretty remarkable. How does that even work?
How does that even work?
It's all about the idea of attractors.
Okay.
An attractor is a stable pattern that the network tends to settle into.
Yeah.
Imagine it like a valley in a landscape.
Okay.
The system rolls down into the valley and stays there.
And those valleys or attractors represent different cell types, right?
You got it.
So one attractor might be a skin cell, while another is a nerve cell.
That's right.
Hmm.
It helps us understand how different types of cells come from the same set of genes,
Right.
just by changing the pattern of activity.
It's like our genome is a dynamic system with a whole bunch of possibilities, not just a static blueprint.
Right.
And the research you sent mentioned that networks with certain properties naturally show order
Yes.
and resemble real genetic networks.
Yes.
Like networks where each gene has two inputs,
Mm-hmm.
or those rich in canalizing functions, where one gene has a dominant effect on others.
Exactly.
It's amazing how simple rules can create such complex, lifelike behaviors.
It really is.
This is blowing my mind. So now I'm curious about fitness landscapes,
Okay.
another big concept in complexity and evolution.
Yeah.
What are those all about?
Imagine a landscape where each point represents a different combination of genes,
Okay.
And the height of each point shows how fit that combination is.
Mm-hmm.
So higher points mean better survival and reproduction.
Okay, so it's like a visual map
Right.
of how well different gene combinations perform.
Yes.
And you mentioned that the shape of this landscape can really affect evolution, right?
That's right.
Yeah.
If it's smooth, evolution can proceed gradually uphill.
Okay.
But if it's rugged, with lots of peaks and valleys, evolution gets a lot tougher.
So if it's like a mountain range,
Yeah.
a population could get stuck on one peak,
Right.
even if there's a higher one somewhere else.
Exactly.
And I imagine those peaks and valleys come from the different constraints on an organism, right?
Exactly. What's good for one trait might be bad for another.
Yeah.
It's like juggling. Improving one thing might make another thing worse.
This ruggedness must make natural selection less effective.
It can.
Like instead of always finding the best solution,
Right.
a population might get stuck on a decent solution that's not the absolute best.
Exactly. And too much mutation can actually lead to an error catastrophe,
Oh, wow.
where beneficial mutations get swamped by harmful ones,
Oh, yeah.
dragging the population down.
So it's all about finding a balance between trying new things through mutations
Yeah.
and holding on to what already works.
Right.
How does life even manage that?
Well, it's a delicate balance that's affected by the shape of the fitness landscape and the mutation rate.
Okay.
Too much mutation and things fall apart.
Yeah.
Too little and you get stuck.
Right.
It's a fascinating puzzle.
This is all incredible.
Yeah.
But how does complexity science apply to things beyond biology?
Mm-hmm.
You mentioned economics and technology earlier.
Yeah,
Do those areas have these fitness landscapes too?
absolutely. Kaufman argues that technologies and economies are also evolving systems. Facing those rugged fitness landscapes,
Yeah.
they have their own constraints and possibilities for breakthroughs and stagnation.
So a new technology is kind of like a species trying to find its place.
Yeah.
Its success depends on how well it fits into the existing landscape
Mm-hmm.
of other technologies and what people need.
That's a great way to think about it.
Yeah.
And Kaufman points out that technological evolution often follows what he calls the Cambrian pattern of diversification.
Okay, remind me what that means again.
After a major innovation, there's a period of rapid diversification
Yeah.
with lots of variations.
Okay.
Think of the early days of cars.
Yeah.
Steam-powered, electric, all kinds of designs competing.
And then over time, a few dominant designs win out.
Right.
And the others fade away.
Yep.
Like survival of the fittest, but for tech.
Precisely.
And just like with complex organisms, the rate of improvement in a technology
Yeah.
tends to slow down as it matures.
Exactly.
That makes sense. As you improve something, the remaining opportunities for improvement become fewer.
Right.
And further,
Extreme.
Kaufman links this to the learning curve pattern.
Yeah.
Each improvement gets progressively harder to achieve.
Right.
It's as if you've already picked the low-hanging fruit.
Exactly.
And this slowing down of improvement is seen in biological evolution too, isn't it?
Yes. As organisms get more complex and specialized, evolution seems to slow down.
Yeah,
It seems like a universal pattern across complex systems.
it does.
Does that mean there's a limit to how much we can improve things,
Yeah.
even with human ingenuity?
It's a humbling thought, isn't it?
It is.
But it also highlights the incredible creativity
Yeah.
and resilience of life and human innovation.
Right.
Even on those rugged landscapes, we're constantly finding new ways to adapt and evolve.
Yeah, absolutely.
Okay, I'm with you so far.
Good.
This whole complexity thing is really changing how I see the world. And, we talked about Kaufman suggesting that understanding complexity could help us redefine what we consider sacred.
Mm-hmm.
What did he mean by that?
It's a fascinating idea.
Yeah.
Kaufman argues that even though science has led us away from traditional religious views,
Right.
we still haven't lost that desire for meaning and purpose.
Yeah, it's like science has taken away the old answers,
Yeah,
but it hasn't given us new ones.
right.
Could complexity help fill that void?
That's exactly what Kaufman thinks.
Hmm.
By seeing how order and meaning can arise from seemingly chaotic systems,
Yeah,
we start to see ourselves as part of something much bigger,
right.
something truly awe-inspiring.
It's like finding the sacred in the patterns of nature,
Yeah.
in the interconnectedness of everything.
Yeah,
Kind of like what we were saying about that Kiowa shield.
precisely.
Hmm.
The return of the shield brought a sense of wholeness and restored worth to the Kiowa people.
Right.
Kaufman believes that our understanding of complexity could do the same for humanity, helping us recover our sense of belonging within the universe.
So it's not about ditching science for spirituality.
Right.
It's about finding a way to bring them together,
Exactly.
to see science as a path to a deeper understanding of the sacred.
That's the heart of it.
Hmm.
And this new perspective could have a big impact on how we live
Right.
and how we build our societies.
Because if we see ourselves as part of this interconnected web of life,
Yeah.
we might be more likely to work towards harmony and sustainability
Right.
rather than just chasing our own self-interest.
It's a powerful concept.
Yeah.
And it's gaining traction as more people become fascinated by complexity.
Right.
And speaking of interconnectedness,
Yeah.
one area where we see complexity at play is in the evolution of technology.
Right. The research you sent showed how complexity helps us understand those patterns of technological innovation and why some technologies just fade away.
One key idea is that technological evolution,
Yeah.
much like biological evolution, plays out on a rugged fitness landscape. Each technology,
Yeah.
like a species and ecosystem, is trying to find its niche.
And just like in nature, there are these trade-offs, right? What's good for one aspect of a technology might be bad for another.
Right.
So it's not so simple to just create the best version of something.
Think about it. You could design a car for incredible speed,
Yeah.
but it might guzzle gas.
Right.
Or you could focus on fuel efficiency.
Right.
But the car might be slow.
So it's about finding that balance,
Yeah.
that sweet spot on the fitness landscape.
Yeah.
And Kaufman said there's a pattern to technological evolution that looks a lot like what we see in biology.
He called it the Cambrian pattern of diversification. After a big innovation, you get this burst of creativity
Right.
with lots of different versions of the new thing.
Yeah.
Like in the early days of computers, there were tons of different designs, operating systems, a real free-for-all.
But then a few dominant designs emerged, kind of like natural selection,
Yeah,
but in the tech world.
exactly.
And as the technology gets more refined, those improvements tend to slow down.
Precisely.
Each new improvement gets harder to achieve.
Yeah.
Just like climbing higher and higher on that fitness landscape,
Right.
Kaufman connects this to the learning curve pattern.
Exactly.
So it's like the easiest improvements happen first,
Right.
and then things get progressively harder,
Right.
like you were saying before about the low-hanging fruit.
Exactly.
And this pattern isn't limited to technology.
Right.
We see it in biological evolution, too.
Yes.
As organisms get more complex and specialized,
Mm.
the pace of evolution often slows down.
It seems like a universal pattern
Yeah,
across complex systems.
it does.
It makes you wonder if there's a limit to how much we can improve things,
Yeah.
even with all our human ingenuity.
It's a humbling thought, but it doesn't diminish how creative
Right.
and resilient humans are.
Absolutely.
Even on those rugged landscapes.
Yeah,
We're always finding new ways to adapt and evolve.
we are.
And speaking of finding new ways,
Yes.
Kaufman also talks about how we can apply these complexity ideas to design and manage organizations.
He does.
Yeah, that was another part of the research that I found really intriguing.
It is interesting.
He has some pretty different ideas about how to create organizations
Yeah.
that are more effective, flexible, and resilient.
One of his key insights is that decentralization is really important.
Okay.
Instead of having one central authority calling all the shots, you distribute decision-making power to smaller,
Yeah.
independent units, what he calls patches.
So instead of a top-down
Yeah,
hierarchical structure,
Right.
you're talking about a more networked,
yeah,
bottom-up approach.
that's right. And Kaufman argues that this decentralized way of doing things
Yeah.
works better in complex environments
Okay.
because it allows organizations to adapt faster to changes.
Makes sense.
Yeah.
Each of those smaller units can respond to their local situation and make decisions that work best for them
Right.
without having to go through layers of bureaucracy.
And exactly. Kaufman has even done research using computer models to see how the size of those patches affects a system's overall performance.
So what do those models show?
They revealed that there's this critical point
Okay.
where the size of the patches determines whether the system is orderly or chaotic. If the patches are too small,
Yeah.
the system acts erratically and can't find a stable solution.
Right.
But if they're just the right size,
What?
the system can quickly discover excellent solutions.
So it's about finding that sweet spot
Yeah.
between too much central control and too much fragmentation.
Exactly. Kaufman calls this receiver-based optimization.
Okay.
Each patch focuses on doing what's best for itself,
Yeah.
even if it doesn't seem like the best choice for the whole system at first glance.
So each part acting in its own self-interest can actually lead to a better outcome for the whole system.
It can, yes.
That's counterintuitive.
Yeah.
But I guess it makes sense if you think about how ecosystems work.
It does.
Yeah.
And it could have major implications for how we design organizations,
Right.
from businesses to governments.
What if decentralization, when done right, could actually lead to better decisions
Yeah.
and greater resilience in the face of all this complexity?
It's a question worth pondering. It just shows how complexity science can make us rethink our assumptions and offer fresh perspectives.
And, when we talk about challenging assumptions and finding new ways to do things,
Yeah.
we have to mention applied molecular evolution.
Absolutely. It's one of the most exciting applications of complexity science.
Yeah.
Revolutionizing fields like medicine, material science,
Right.
and even agriculture.
It's all about using natural selection to discover and optimize molecules, right?
That's the idea. Instead of trying to design a molecule from scratch, which is super hard,
Yeah.
you create a massive library of random molecules and then test them to find the ones with the properties you're looking for.
It's like speeding up natural selection in a lab.
Yeah,
Finding molecules that would have taken nature millions of years to evolve.
exactly.
And this approach has already led to some incredible breakthroughs.
It has. It's being used to develop new drugs,
Right?
create new materials, and even design new enzymes for industrial applications.
One example that really blew my mind
Yeah.
was the creation of catalytic antibodies, what are called abzymes.
Yes.
They're basically antibodies that can speed up chemical reactions.
They are, and they're created by first making antibodies that bind really tightly to a molecule
Okay.
that looks like the transition state of a chemical reaction.
Wait, remind me what the transition state is again.
It's that unstable, high-energy state that a molecule has to go through in order for a reaction to happen.
Oh, right.
Yeah.
So by binding to a molecule that mimics,
Yes.
making the reaction more likely to occur.
Exactly. It's a super clever way to use evolution as a design tool.
It is. And applied molecular evolution isn't just limited to enzymes.
Right.
It's being used to design all sorts of new molecules.
It is.
From peptides that can target specific receptors to DNA molecules that can act as sensors.
It's just the beginning. As we learn more about complexity and evolution, we can use that knowledge to design even more sophisticated and powerful molecular tools.
This is incredible.
It is, yeah.
So we've talked about self-organization, the edge of chaos,
Yes.
the evolution of complexity, and everything from organisms to technologies.
Right.
But what about how this all connects back to that idea of the sacred
Yeah.
that we were discussing earlier?
That's a great point.
Yeah.
One of the things that makes complexity science so compelling is that it doesn't just offer a new way of understanding the world. It also touches on those deeper questions about meaning and purpose.
Right, because if we're part of this vast,
Yeah.
interconnected web of complexity,
Yeah.
maybe that tells us something about our place in the universe.
Exactly. It's like finding a new kind of reverence for the world around us, a sense of awe at the intricate dance of order and chaos
Yeah.
that gives rise to everything we know.
And maybe that sense of awe can inspire us to act differently, to be more responsible stewards of this amazing planet we call home.
It's a powerful thought, isn't it? That by understanding complexity,
Yeah.
we might not only unlock new scientific knowledge, but also rediscover a sense of wonder and connection to something much greater than ourselves.
Yeah. Okay, so we've covered a lot of ground here,
We have.
but there are a few things I want to circle back to.
Okay.
Earlier, you mentioned genomic networks
Yeah.
and how they're like a network of light bulbs.
Yes.
Can you break that down for me again?
Sure.
It seemed like a really important piece of the complexity puzzle.
It is. Imagine a huge network of light bulbs, each one representing a gene,
Yeah.
and these light bulbs can be either on or off, showing whether the gene is active or not.
And they're all connected in these crazy ways,
They
with some bulbs turning others on or off.
Exactly.
Now picture this network of light bulbs constantly flickering,
Yes.
on and off,
Yeah.
based on simple rules.
Right.
Amazingly, those simple rules,
Yeah.
built into how the bulbs are connected,
Right.
can create stable patterns of activity.
They can.
So it's not just random flickering.
Right.
There's a hidden order in how those light bulbs behave.
And that's where attractors come in.
Okay.
An attractor is like a magnet pulling the network towards a specific pattern of activity.
Yeah.
Think of it like a valley in a landscape,
Right.
a stable state that the system wants to settle into.
And each of those valleys or attractors represents a different cell type, right?
That's the idea.
Like one attractor might be a skin cell, another a nerve cell, and so on.
That's the gist of it.
Different cell types emerge from the same set of genes.
Yeah.
just by changing the pattern of activity within the network.
Right.
So it's not like our genome is a fixed blueprint.
Right.
It's more like a system with a bunch of possible states.
Yeah.
And the research you sent talked about how networks with certain properties tend to naturally show order
Yes.
and look like real genetic networks.
Yes. Like having 2 inputs per gene.
Right.
Or having a lot of those canalizing functions where one gene has a strong influence over others.
It's incredible how simple rules can lead to complex behavior that mirrors real life.
It really is.
It really is. Okay, now I want to zoom out from genes
Sure.
and talk about ecosystems and economies.
All right.
You said those are complex systems too, right?
Absolutely. One of the most fascinating ideas in complexity science
Yeah.
is that both ecosystems and economies are constantly evolving,
Right.
adapting and transforming.
It's like a never-ending dance.
Yeah.
With species and technologies interacting, competing, and shaping each other.
And a major part of this dance is coevolution.
Okay.
As one species evolves, it puts pressure on others to adapt.
Right. And vice versa.
Yeah.
This creates a constant feedback loop,
Okay.
driving innovation and diversity.
Like in those predator-prey relationships we talked about earlier.
Exactly.
Predators become stealthier,
Mhm.
prey become faster, and so on.
Exactly. And it's not just nature.
Right.
We see it in technology all the time.
Yeah.
The development of computer hardware and software is
Yeah.
a great example. They're always pushing each other to become faster.
Yeah.
So it's like a fractal pattern. It's
Exactly.
the same dynamics playing out on different scales.
And one of the key things that complexity science tells us
Yeah.
is that ecosystems, just like economies,
Yeah.
are most stable and resilient
Right.
when they find that balance between order and chaos.
There it is again, that sweet spot,
Yeah.
that edge of chaos.
That edge of chaos, it seems to be everywhere.
It's a common thread throughout complexity.
Yeah.
Too much order and the system becomes rigid
Yeah.
and vulnerable to collapse.
Yeah.
Too much chaos and it's constantly disrupted.
Right.
But at the edge of chaos,
Yeah.
there's a balance between stability and adaptability, the sweet spot for a system to thrive and evolve.
And Kaufman suggests that there are some interesting ways that complex systems achieve that balance.
Yes.
We talked about this idea of patches, right?
Right.
Breaking a big problem into smaller, more manageable parts.
That's right.
It's something we see everywhere in nature
Yeah.
and in human organizations. We do.
Cells form tissues.
Yes.
Tissues form organs,
Yeah.
and so on. Companies have departments. Departments have teams, and so on.
Exactly.
And by focusing on a smaller piece of the puzzle, each patch can do its best work,
Right.
which makes the whole system more efficient and adaptable.
Precisely. The key is finding the right size for those patches.
Right.
If they're too small, things get fragmented.
Okay.
Too large, and you lose the benefits of local adaptation.
Right.
It's like Goldilocks, not too big, not too small.
Just right. And Kaufman's research has shown
Yeah.
that there's this tipping point when it comes to patch size.
Yes. If the patches are too small,
Yeah.
the system behaves erratically.
Okay.
But if they're the right size,
Yeah.
the system can quickly find excellent solutions.
He calls this receiver-based optimization, right?
You got it.
Where each patch just focuses on doing what's best for itself.
Yeah.
Even if it doesn't seem like the best thing for the whole system at first.
Right.
And somehow, all these individual parts acting in their own self-interest
Yeah,
can create a surprisingly good outcome for the whole system.
they can.
It's like that invisible hand of the market idea,
Yes.
where people pursuing their own goals
Right.
can end up creating a more prosperous economy overall.
That's a great analogy. So it seems like there's a hidden wisdom in decentralization
Right.
and letting the parts figure things out locally
Yeah.
rather than trying to control everything from the top down.
It's a fascinating idea that could change how we think about designing and managing everything,
It could.
from businesses to governments.
Yeah.
What if a more decentralized, patch-based approach
Yeah.
actually led to more adaptability, resilience, and innovation?
It's a question worth exploring, and it just goes to show how complexity science can make us challenge our assumptions and open up new possibilities.
This deep dive into complexity science has been mind-blowing.
It is fascinating.
It's like a whole new way of seeing the world.
Yeah.
And I'm already noticing those patterns of complexity everywhere I look.
Yeah, me too.
So for anyone listening, we encourage you to keep exploring this fascinating field.
I agree.
You might be surprised at what you discover
You might.
about the intricate dance of order and chaos
Yeah.
that shapes everything around us.
It really does.
And who knows, maybe you'll even find your own sense of this sacred, in the beauty of complexity.
You might. That's a great point.
Well, that's all the time we have for today,
Okay.
but we hope this deep dive has sparked your curiosity to learn even more.
It's a fascinating field.
Thanks for joining us.
Thanks for having me.